Uh, Hello everyone, am I audible? Am I audible? Hello. Okay. Let's start with today's session. So last Friday I had uploaded the week 5 related video. If you go to the problem sheet link, I think that will be there. I have taken about photogrammetry and introduction to microwave remote sensing. So, in today's session, we will be covering the remaining part of the microwave remote sensing and the supervised classification, how to do it in QGIS. I think the thermal remote sensing part was covered by the other TA in detail. Okay, so I'll start today's session. Okay, in the last week session, I solved several problems related to the photogrammetry. So, problems related to scales, how to find the height of the tower by using the concept of relief displacement. Then, if there is a parallax in the image, by using the parallax, how can we estimate how much the point has moved, or we can also estimate the height of the tower as well, and we can also estimate the distance between 2 points, and if the terrain is undulated, how to estimate the distance, then number of photographs that are necessary to complete a aerial survey, and histogram equalization. I have discussed about the corrected demo. So there was a issue with the data type involved, so I was saving it as integer 16 data type, but since we are converting from 16-bit to 8-bit, the saving type should be 8-bit type. So that was the error. So I have uploaded the correct procedure for that. Then I also did a very quick unsupervised classification demo in QGIS, and followed by change detection, how to do it in QGIS. Then a brief about remote sensing. So in today's session, we will see about how to do the supervised classification using the CP tool in QGIS. Then coming to microwave remote sensing, we'll discuss about radar geometry, radar resolution. So there are two types of resolution. Then what is meant by synthetic aperture radar. Then radar equation and some problems related to the maximum, how to determine the maximum range of the radar. Then how the microwave interact with the Earth's surface. We'll discuss how it is interacting. Then what is the relation between roughness and scattering, and the wavelength as well as the penetration power of the microwaves. Then what are the different types of polarization and its types, and what are the geometric distortions in microwave image. Then one interesting, very interesting application, that is interferometry by using the microwave data. So I will show you a case study which I came across very recently. So we'll start with the supervised classification. So to reiterate the theoretical part, in supervised classification, we need to have the training data. So we will collect the training data, then we will use the spectral signature of the training data in the classification algorithms to classify the remaining part of the area. And similarly, after classification, we will have some points or polygons as testing data, and we will test how much how accurate is our classification. So let us see how to do it in QGIS. So I have a Landsat 5 data. So it has been clipped to a very small extent. So the given extent was much more bigger. So here there are band 1 to band 7 of the Landsat 5. So I'm loading the Landsat 5 data. And just to give a very quick topographic visualization. So this is the southernmost point of India. So it is between Kerala and Tamil Nadu. So this is the Western Ghats that you are seeing. So our data is between Tamil Nadu and Kerala. So if we see the quickly the land use types, so we have some urban settlements. Then we have a lot of agricultural area. Then we have barren lands, and towards the south near the coast, if you see, these are all the salt pans, and we have a very good cover of forest as well. So whenever you are going to do a supervised classification, the first thing that we need to know is we should know what is the level of classification that we are going to do, and what are all the classes that we are interested in. So whatever I told just now, these are all level 1 classes. So these are all the classes that we are currently interested in. So once we import the data, we should go to SCP tool and we need to create a new band set. So I will remove the Google satellite from this, otherwise that will also be counted as a band. So once I open the SCP tool, so this is the band set, and you just need to click on this refresh list. So whatever data that is opened here, that will be displayed here. So band 1 to band 7. Now we need to select everything, and then you need to give this plus icon. So add to band set. So it will come here. Now what we need to do is we need to tell what data does it belong to. So what is the wavelength range. So currently everything is like 1 to 6. So we need to click on this wavelength quick settings, then look for Landsat 4.5. So our thing is Landsat 5. So we have Landsat 4.5 thematic mapper bands. So once we assign that, the central wavelength of the Landsat 4.5 will get assigned to this bands. Now we need to create a virtual raster of this band set. So I'm going to click on this checkbox and then I'm going to give run. So this dialog box will open. So we need to save it in a separate folder. So I'm making a new folder. So I have selected the folder. So and it has created our virtual band set. So I'll remove all the others from the view. So it has created a virtual band set. That is our, it will contain band 1 to band 7. It is basically our stack only. Now we need to put a false color composite. So 4, 3 and 2. This is for NIR, then red and then green channel. Then I'm going to give apply. So from this you can see there is so much red in this. So which means there is a lot of vegetation in this area. Because in false color composite your NIR will be in red. So and in agriculture you can see a different tone of data. So now I'll bring back the Google satellite. So you can see this is agriculture, and then if we go towards the forest area, so the red color is different for both agriculture and forest. And for urban it will be gray to bluish or cyan in color. And these are all the fallow lands, which means agriculture is currently not yet being done, but these are all agricultural areas only. So these are all agricultural area. So once we get our band set, so next thing is we need to create a training data. So what I will do is I will open the SCP doc. So right click on this panel. So we just need to select the SCP doc panel, and here you can see training input. So I'm clicking on that. Now we need to create a new training input. So I'm going to save it as training sample, and I have saved this. Now what we have to do is we need to select our classes. So for that, if you see here, this is called as so here this tool. So create a ROI polygon, which means a region of interest polygon. So what we are going to do is we are going to select pure pixels of each land use class. So pure pixel means so for water I'm going to the ocean and I'm going to the darkest part so that there is not influence from any other area. So I'm going to select one draw one polygon, then right click on it. So I have closed. So I'm going to give my class name as water and subclass. So if you are doing a level 2 classification, we can also give a second level of classification. So since we are doing level 1, I'm just going to give level 1. So I'm going to select different water pixels. It is not loading. So once you select the polygons, you need to save temporary ROI to training input. So whenever you select a polygon, you just need to click every time this save option. So what it will do is it will take our the surface reflectance from this area, calculate the average surface reflectance within this area, and then it will display here. So we can change it to blue color. So this is my first polygon, and this has disappeared. So this is my second polygon. So there is a reservoir, so we can take pixels from here also. So this is my third. And when you are selecting from pixels like this, you need to be very careful, because you can see lot of mixing is happening here. So these are all not pure pixels, so it's better to avoid them. But in some places you can see dark pixels, so in that case you can select a very small area and then you can make a polygon. So and if you observe, I am not taking from one single place, I am looking for different areas. So your training pixels should be selected such that you are having a representative training data from your whole study area. So once we are done, we can select all this and then merge it into single data. So if I merge, so it will take average of all the values and then give us a single polygon. So rest of the things we can delete later. Okay, so this is the merged water pixel. So then next is our agricultural area. So I'm changing the MC ID to 2 and the class ID to 1, and I'm going to give agriculture, and similarly class ID also agriculture. So this is a very tedious process. You should be little patient, and then you need to take the representative sample. Okay, let's say this is for agriculture. So similarly, you need to do for each and every class. So the more the number of training pixels, the more will be your accuracy. So let's say once you have done for all the classes, what you can do is here there is an option, add highlighted signature to spectral signature plot. You can click that. So before that, you should select water and agriculture. Then you should click this. So if you see this, this is the spectral signature plot. I think the color is okay. So you can see this is dotted lines are band 1, band 2, band 3, band 4, band 5, and band 6. So you have the entire spectrum. It has taken the sample points, and you can see in the fourth band your vegetation is very high, and similarly your water is decreasing from your blue to your SWIR band. So like this, when you have the other classes also, you will have this kind of a plot. Now I will show one important phenomenon, that is where the mixing of pixels happen. So here I will take a class number 3 and then I will put fallow. Okay. So you can see here now three plots have come and your fallow has also come. So these are also agricultural lands, but they are currently not cultivated. So when you see in certain part of the spectral signature plot, these bands cross each other. So ideally they should not cross each other, and if at all it is crossing, it should be very minimal. So when you are selecting the training pixels, you need to plot the spectral signature plot and check whether this kind of mixing is there or not. So when we get the output of the classification, you will notice that some fallow land will be classified as agriculture and some agriculture will be classified as fallow land because of this mixing. So this is one of the crucial points, crucial point where the error in your classification will be generated. But we cannot avoid it. But we should make sure that it should be minimum. So that depends on how we are how accurately we are selecting our training pixels. So anyone has doubts until this point? Hello. Okay. So I will remove this training pixels, and I already have a training set. So I'm going to import that. So I have already saved it as a training document. So I'm just going to open it. So you can see the number of polygons that I have chosen. So and I'm going to plot the spectral plot of it. So you can see there is a lot of mixing that's going to happen. It's not very perfect. So once we are done with this training samples, we need to go to SCP again, band processing, classification. So this dialog box will open. And here our input band set what we have created is band set 1, and we are going to use MCID for our classification. So that is the main class ID. And if you are going to do level 2, you can select, you can uncheck this and then use this. And here you can see different algorithms are there. So here in QGIS and SCP plugin, we have three algorithms. One is minimum distance, maximum likelihood, and spectral angle mapping. So for supervised classification, either you can go for a maximum likelihood or spectral mapping for a very good result. So I'm going to go with maximum likelihood. It's a probability based method. And I'm just going to keep the threshold as a 0.01. And I will be using the algorithm to do the classification. So I have checked the algorithm. Then I need the output of the classification report. I am going to check that also. And then I am going to click on run. So we need to save it in a folder. Supervised classification. So it has completed the classification. So you can see this is the output of the classification, and to show you, yeah. So you can see the reservoir. Close this also. So you have agriculture, forest, urban, barren, and water. So if you see the water body, so you can see the edges are also captured very nicely. And if I go to the barren land, see there is a lot of mixing. So it's not a barren land, but it is classified as barren land. So that's all source of errors. And here you can see mixing that's happening. So this is completely a barren land, but you can see red pixels. Red means urban. So, and here you can see the agriculture area. So some of the agriculture areas is also mixing with barren. So here barren includes the actual barren lands, the wastelands, then your fallow lands, and the salt pans also. So that's why have lot of mixing here. And the salt pans are captured more or less quite accurately. And let's come to your urban area. So you'll have a lot of mixing between your barren and urban. So both will have a similar spectral signature when you are doing it in Landsat images. So you can see a lot of mixing happening there. And this is also another settlement. So it's captured reasonably well. Let's now calculate the accuracy. So to calculate the accuracy, again you need to go to SCP, then post processing, you have accuracy. So the way you select the training data, you should also have the testing data. So what I have done is I have created a testing polygon beforehand itself. So before I begin the classification, the first thing that I do is I created the accuracy assessment polygons. So you can see these are all the polygons that I have created for classification. So for each class, there will be n number of polygons. So if I go to the attribute table, you can see. So there are about 50 polygons. So 10 for each class I have taken. So once we load that polygons, you can go to SCP, band processing, classification. Sorry, not classification, post processing and accuracy. So first the input is select the classification to assess, which is our classified image. Then reference vector or raster. So I have the accuracy polygon. So that is accuracy polygon that has come, and the vector ID has also come. Use no data value as 0, and then I'm going to run it. So once you finish the accuracy assessment, you can see the confusion matrix that is generated here. So if you see here, it is around 97% accurate, although a lot of mixing is happening since our maybe the area is big or the number of testing polygons are less. So it is overall accuracy is 97% and the kappa hat classification is 0.96, and this is your confusion matrix. Here you have your producer accuracy, then your user accuracy, and kappa hat for each class. So this is how you can make use of QGIS to make a supervised classification. So anybody has any questions, doubts?
Sir,
Yeah.
when we do that this accuracy test, so
Yes.
we know that we are taking the those polygon for the sample for water or these all things.
Yeah.
So and we are also checking the same thing for the accuracy also.
No,
It
no,
is
no. These are not the same polygons.
okay.
So if I just load the training, just a minute. So you can see there are a lot more polygons for training. It's not the same polygons. So there are so
Okay,
many other
okay.
polygons.
It's basically check the when the signature is mixing for those areas mainly, no?
No, it does not check the signature here. What it does is, so here we have given some IDs, no, 1, 2, 3, 4, 5.
Yes.
So this is our classification IDs. So in accuracy ID, in accuracy data, what I would have done is, I also have the same ID.
Okay.
So when we are creating this polygon, what we will do is, when we are creating the accuracy polygons, so what we will do is, it will take the average for classification. It will take the average value from this particular area, and in
Okay.
accuracy we will assign the class. So this entire area should be maybe forest, so this should be number 2.
Okay. Okay.
So it will check
Thank you.
each pixel with the polygon.
Okay. Okay.
So
Thank you,
that
sir.
is a,
Thank
yeah. Okay, so this is with respect to supervised classification and unsupervised classification in the last class. So So in the last session, I just briefly introduced what is microwave remote sensing and why it is very useful for us. And I would have stopped at introduction to the radar geometry. So today we'll continue with the radar geometry. So in radar geometry, so let's assume here is the aircraft or the satellite, and you have the sensor, and it is basically a side-looking uh, sensor. So when the sensor is having a side looking, so it is emitting the radio waves, and when the radio waves spread, it does not go directly like a single ray of beam. So if this is the source, so it is going to expand in your entire field of view, and it's going to have a 3D shape like this. So because of this spread, your near range and your far range resolution will not be the same, and you will also see the resultant will be a rectangular pixel because of this side looking type of sensor. And we have two types of resolution in this, so we'll come to that. So first term that you need to understand in the radar geometry is the range. So range is the distance from the sensor to the target, and you should know that this range is the slant range. So it is not projected to the ground surface. So it is not the exact horizontal distance. It is the slant range. And we second thing we have is the look angle or the off nadir angle. So with respect to your nadir line, how much the sensor is tilted away. So that is your off looking or the nadir angle. And if you take a 90 minus theta, that will be your depression angle. So they are all interrelated. Then once it hits your sensor, when you draw a perpendicular normal from the uh, terrain, and you measure the angle with respect to your slant range, that is your incidence angle. And this incidence angle varies from place to place, and it also varies with respect to the curvature of the earth. So if you see here, normal to the surface is this one, and you have a very wide incidence angle. And if it is a sloping surface, you will have a very small incidence angle. So if it is like this, and if I draw a normal, and your this is your incoming pulse. So this angle will be very small, and your theta varies from every pixel to pixel. And 90 minus your incidence angle will be your grazing angle, that is with respect to your ground. So if you project this slant range to the ground, that distance is called as the ground range. So this distance, that is the your ground range, and this is your slant range. So these are the two different types of ranges. Next is the incidence angle. So I have already defined this. So when the surface curvature effects are neglected, the look angle is equal to the incidence angle. So your this angle and incidence angle will be equal. So they are alternate angles. And when your orbital platform is at a very much up in the altitude, which has a very high altitude, the surface curvature should be taken into account. So, and this is the different angles which I just described through the diagram. So in case one, it is exactly perpendicular to the surface, and if it is a hill slope, you are having very less incidence angle, and in this case you have a very wide incidence angle. And in the third case, if you see, the pulse is moving away from the sensor. So if it is a monostatic radar, that is, this is your source and as well as this is your receiver. So this particular backscatter will not reach the sensor, and this portion will appear very dark in color. So you will see all the shadows in the image, in your microwave data. So next part is your radar resolution. So first is the range resolution. So by definition, so resolution here is defined as the separation between two closest features that can still be resolved in the final image. So I will show what is how this range resolution is defined. The sentence meaning I have an illustration to show. I will show that. So consider two target points that are separated in the distance by a distance of small xr. So your radar will send a pulse to the target, and then it has to receive it back. So if you consider the distance as d, it will be 2 times d. So here it is xr, so it will be 2 times of xr. And the speed of the pulse is the speed of the light. So if you divide a distance by the speed, you will get what is the time that is taken for the pulse to travel from the sensor to the target and from target to the sensor. So this time we will note down. And the radar waves are not usually transmitted continuously. So it will be first it will transmit a pulse, then it will be idle for some seconds, and then later it will transmit the second pulse. So it will be a short burst of pulse. And two features can be discriminated only if the returning pulse is received later than your first pulse. So I will show that with this example. So let's say two targets are there, and we have sent two pulses. So this is your return pulse. So if the targets are separated by a considerable distance, you will identify two separate pulses, and you can decipher that there are two objects that are at this particular distance. But if the objects are very close to each other, your first pulse will hit your first target and then it will return, and by the time your second pulse travels, hits the targets, and it will have a overlap with your first pulse. And your radar will consider these two pulses as a single pulse only. So you will not be able to decipher that there are two objects, but rather you will be seeing that there can be only one object that is coming in. So this is when they are at some distance, and this is your first pulse, and your second pulse is just coming back at the tail of your first pulse. So then also it will not be able to distinguish. And if it is much closer, then you will not then your radar pulse may be something like this. So this is your first pulse and this is your second pulse, so you will not be able to decipher two different objects. So this is what I have explained. So this is your first reflected pulse from target 1, then second reflected pulse from the target 2, and this is your transmitted pulse, initial pulse. So you will be able to decipher two different objects. But if the targets are close to each other, your transmitted pulse is one, but your receiving pulse will be overlapped with your first pulse, so you will not be able to identify two different scatterers. Rather, you will be able to identify only one. So, anybody has any doubt in this?
Just a quick question.
Yeah,
Can you please go back to the previous couple of slides, like where we have seen look angle and the incident angle
yeah.
just before one? Yeah. So here, so it's always like the look angle plus the incidence angle would be equal to 180 degrees, or it may differ it sometimes.
Look angle plus
Incidence angle,
incidence angle.
or the other way, depression angle plus gazing angle is equal to 180 degrees.
Depression angle plus
Sorry,
grazing.
90 degrees. It's 90 degrees.
Yeah, it should be equal to 90 degrees.
It's always right.
Yes.
Okay.
So they are all alternate angles only, so it should equal 90 degrees. But the magnitude of the depression angle and the incidence angle, that will differ.
Magnitude, when you say like
Like when you have an undulating terrain, so maybe your depression angle will be very high, but your incidence angle will be very less.
okay,
So let's
okay,
say 80 degree and 10 degree, something like that.
okay.
Okay. So next is the so this is what I just briefly described as a derivation. So it is so XR is the slant range. So it is speed is equal to distance by time. So this is the phenomenon that's written here. So tau is your time required for the pulse to travel to the target and to return back, and c is the speed of the light, and it is going to travel two times the distance, so divided by two. But this is the slant range from the sensor to the target. Now what we really need is we need the ground range from the another point. How much away is the target? So we are going to resolve this triangle. So when you resolve this triangle, you can project your so this will be your theta. So when you are projecting to the ground surface, this will be cos of 90 minus theta. So if you are considering this as your theta, so this will be 90 minus theta. And if you project this line onto the ground, so it should be 90 cos 90 minus theta, which is nothing but your sine theta. So that is what is written here. So your ground range xg is same formula, just you need to divide it by sine theta. And the theta that we are using is the local incidence angle, so which will differ from pixel to pixel. Okay, now you note down both these formulas, and we will be solving a problem related to the ground range of the sensor. I hope you have noted down. Okay. So a SLAR system, that is a type of radar. It transmits a pulse over a duration of zero point 0.2 microsecond at a depression angle of 23 degrees centigrade. What would be the ground range resolution? And you can assume the surface to be flat. So can you quickly calculate and tell me?
So I haven't reached to complete calculation, but it would be xg equal to delta t multiplied by 0.2 by sine 23 degrees.
Okay, let me check. So if you see the question, depression angle is given, incidence angle is not given. So in this question, uh, your time is given, depression angle is given, and assume the surface to be flat. So your ground range resolution will be xg is equal to c tau divided by 2 sine theta. Theta is the local incidence angle. And from the diagram, if you see, so this is the exposure station, this is the horizontal, and this is the perpendicular, and this is the target. So this is your theta, but this angle is given as 23 degrees. So now we need to find this theta. So it is 180 minus theta minus 23 degree. Sorry. So 180 degree is equal to 90 plus 23 plus theta. So your theta is equal to 67 degrees. So this is your local incidence angle. So once you get it, you can find out. So xg is equal to c is 3 into 10 to the power of 8 meter per second, and time is given as a 0.2 microsecond. So 10 power minus 6 seconds divided by 2 into sine 67 degrees. So your ground range resolution is 32.59 meters, approximately 33 meters. 32.59, maybe some decimal place issue. Okay, it's almost approximately 33 meters. Okay, so this is one type of problem. So this is how you can calculate your range resolution. So next part is the azimuth resolution. So your azimuth resolution corresponds to your width of the beam. So your width of the beam is represented by beta. So as I told you earlier, so your beam is going to span away from your sensor, and it's going to cover certain part of the ground, and it's going to be different at the near range, and it's going to be different at your far range. So as the beam spreads on the ground, the spatial resolution varies in the ground range direction. So this is the ground range direction, and you can see. So there are three objects spaced at equal distance from each other at both point A and point B. So they both are at same distance in both the points. But you can see that in the near range, you will be able to identify only one target, but in the far range, you can see three targets. So this means that your azimuth resolution at the near range is higher than your far range, because you are able to detect individual objects in the near range, but you are unable to distinguish these three objects in your far range. And azimuth resolution is a function of your height of the platform, at what altitude it is, and at what angle it is looking your surface, and how much is the length of your antenna, that is the source. The radar pulse will be emitted from your antenna, and what is the wavelength of microwave band that you are using. So these are all the factors which determine your azimuth resolution. And we can calculate the azimuth resolution R as h lambda by d cos theta. So I'm not going into the details of derivation. So here one important concept comes into picture. What is the difference between real aperture radar and synthetic aperture radar? So by solving the examples, we will be able to say why synthetic aperture radar is needed and what is the problem with the real aperture radar. So in this example, first is a radar has an operating wavelength of 3 centimeter, and it is positioned at an altitude of 700 kilometers. So if the look angle is 30 degrees, and the antenna length is 50-meter, then what would be the azimuth resolution of the data that is obtained? So can you substitute and find out what is the azimuth resolution for the first problem? So here theta is directly the look angle of the satellite. So be careful with the units. So anybody is calculating? Okay. So your azimuth resolution is equal to h lambda by d cos theta. So if I substitute, so h is 700 into 10 power 3. I'm having everything in meters. So your wavelength is 3 centimeter into 10 to the power minus 2 meters divided by antenna length is 15 meters into cos 30 degree. So if we approximately work out, it is around 484.97 meters resolution. So you can see, if you have an antenna length of 50 meters and you are operating in 3 centimeter wavelength with a look angle of 30 degrees, you will achieve only 484.97 meters of range azimuth resolution, which is very very coarse. For fine applications, we need to have a range resolution that is azimuth resolution that is much less. For example, your RISAT, I don't know how many of you have heard it. Resat 1 is a satellite by the ISRO itself. Uh, it has a azimuth resolution of the order up to 6 to 10 meters. So we will see that. Now the second problem. So I'm going to fix my azimuth resolution. So I want my azimuth resolution to be 5 meters, and I'm going to have the all the other parameters remain the same. So your wavelength is 3 centimeter, altitude height is the same, look angle is also the same. Now I'm going to calculate what is the length of antenna that is required. So if I calculate that, so this is 5 meters, 700 into 10 power 3 into 3 into 10 to the power minus 2 divided by, I need d cos 30. So if I calculate this, 4849.74 meters, which is 4 kilometers in length. So you need an antenna length of 4 kilometer. Is it possible to have such a long antenna in the space? It's not possible, right? So this is the problem with your real aperture radars. So you will not be able to get a very fine azimuth resolution. So you will have very coarse resolution. So what they have done is there is a concept of synthetic aperture radar. So the inference from both of this problem is you will not be able to have a very long antenna up in the space. So it is practically not possible. So how to increase the azimuth resolution? So for a fixed wavelength, azimuth resolution can be increased by decreasing the platform height, but it has its own disadvantages. And another way of increasing the azimuth resolution is increasing the antenna length, but we can do it only up to a certain extent, but you cannot do it for a very large extent. So in case of airborne radar, the antenna length is usually 1 to 2 meters, and for spaceborne it is 5 to 15 meters. So I told about the RISAT one. It has an azimuth resolution of 6.29 meters, and RadarSat is another satellite, microwave satellite. It has a azimuth resolution of 15 meters. So how is this possible? So this is the different modes of acquiring. So you can see here for the Indian satellite, your azimuth resolution. High resolution is 1 meter, then fine resolution is 3 meters, then you have 9 meters, then 21 meters, and up to 41 meters. So this is for RISAT 1. So here is where the concept of a synthetic aperture radar comes into picture. So what we are doing is we are virtually increasing the antenna length. So we are not increasing it physically, we are virtually increasing it. How we are doing it? So if our satellite passes from the point A to B, and this is our target object. So when it passes from A to B, your sensor is going to look at the same object again and again. So it will be overlapping your near range, far range, that entire width that's going to overlap with each other. So that is called as a multi-look. And we will be able to virtually synthesize this entire length. So if you add up all this, you will get your synthetic length of the antenna, which is your LS. And by doing this, we will be able to achieve a virtually very high length, which will increase our which will enhance our azimuth resolution. So I have discussed the theory in this. So here the antenna starts to transmit the signal at position A and continues till the position B. The backscatter from the target C can be recorded during the entire time range. So continuously it's going to record the return pulse from the object C. So objects at the far range will be illuminated for a longer time than the objects at the near range. So here your azimuth resolution will be different. Here it is going to be different. So now you can calculate this azimuth resolution for this particular data. So here a synthetic aperture length is 1 kilometer. All the other parameters remain the same. So what is the azimuth resolution that is achieved? So can somebody quickly calculate? So okay, that will be 700 into 3 into 10 power minus 2, 1 into cos 30. That's going to be equal to 24.24 meters. So this is the uh, azimuth resolution that you will be able to achieve with the synthetic length of 1 kilometer. So is this concept clear? Hello? Okay. The next part of the microwave remote sensing is the what is the geometry of your radar is the radar equation. So here the radar equation power received, PR is power received, which is equal to power transmitted into G is the gain of the antenna into sigma is the radar cross section, AE is the effective aperture of the receiving area, then divided by 4 pi square into r to the power 4. R is your range. So if you see here, if you want to receive, so if your range needs to be very high, it depends on your transmitting power. If your transmitting power is high, your range is going to be high because it is directly proportional, and it also depends on the radar cross section. So how much your radar is able to receive, and effective aperture of the receiving antenna. So that is with respect to your radar cross section, and the R is your slant range. So this is the fundamental equation from where we will be able to find out what is going to be the range of the radar given the parameters. So we will solve one problem from two problems for the radar equation. So if you see, the transmitting power is 250 kilowatt. It is very high. And if you see the receiving signal, that is 10 to the power of minus 12 watt. So it is like n number of times lower than your input power. So this is one of the disadvantages where you need to have a very high input power source to get a detectable signal, and all the other parameters are given. So we need to find out what is the maximum range. So how far your radar will be able to detect if some object is present, how far that object can be. So here power of the minimum detectable signal is given. So your range of the target will be at the maximum range when your radar is able to detect the minimum amount of energy. So there will be a threshold that will be set beyond which we will not be able to recognize anything. So we will solve this problem. So your radar equation is and peak power transmitted is 250 kilowatt. Then minimum detectable signal 10 to the power minus 12 watt. Radar cross section is 4 meter square. This is 4 meter square. Okay, now the range max we need to find out. So we can substitute the equation. So 10 power minus 12 is equal to 250 into 10 power 3. Gain is 4000 into so R is the only unknown. So if we calculate, so it is 158633.559 meters. So if I convert it into kilometers, it is 158 kilometers. So whatever the object that is above more than away from this 158 kilometers, you will not be able to recognize it. And in the second problem, so there is a relation between your gain of the antenna and your effective aperture, because if this is the surface and here is your target, whenever the backscattering is going to happen, it is going to emit in the form of a hemisphere in case of your specular reflector, not specular reflector, a perfect diffuse reflector. So it is going to emit in the form of a hemisphere. But since your antenna is like side looking, not all the backscatter energy from this entire hemisphere is going to reach your sensor. So let's say maybe from this 180 degree, maybe only like 70 to 80 degrees of the within this bandwidth, it's going to reach your sensor. So whatever is that area that's going to receive, that is called as your effective aperture area, and it is calculated as a gain of your antenna, and they are establishing a relationship between these two parameters. And if you substitute, you can substitute instead of your gain of the antenna, you can use this relation and bring it in terms of wavelength to determine your range. So when we do that, the same formula changes to this format. So we are bringing range here, and your wavelength is here. So if you want a higher range, you need to increase your wavelength also. So that is also one of the inferences from this formula. Now we can solve this question. So we need to again calculate the maximum range, but here the operating frequency is given. So frequency is related to the speed of light and wavelength. So we will be able to find out what is the wavelength that's used. And peak power transmitted is 400 kilowatt. The effective aperture of the receiving area is given. Radar cross section is given, and the minimum power that is detectable is 10 power minus 10 watt. So similar thing, but here we are bringing the wavelength into the picture. So we will solve this question. So your frequency is 10 gigahertz. So peak power transmitted is 400 kilowatt, Your effective aperture area is 5 meter square. Your radar cross section is 13 meter square, and minimum power detectable. And your maximum range that can be for the given radar is 10 into giga is 10 power 9, the whole square into, so this is power received, 10 to the power minus 10 to the power of 1 by 4. So if you find out this, it is 127,127,619.55 meters. So your range maximum for this particular radar is 127.61 kilometers. So this is how you can make use of the radar equation to determine what is the range of the radar. Okay. So next part of the microwave remote sensing is how does the microwaves interact with your earth features. So your microwaves basically depends on the interaction of microwaves depends on how rough is the surfaces. So it's all about roughness in this uh, part of the remote sensing. So previously in optical remote sensing, we saw what is the reflectance from the surface. Now we are going to see how the roughness is going to influence the microwaves. So we have three different mechanisms by which your microwaves can interact. So first is the rough surface scattering, or you can also call it as a single bounce. So when you have a simple rough surface, so your this is your uh, transmitted pulse, and this is going to be the uh, scattered pulse because of the roughness, and this is going to reach your receiver. And second type of interaction is a double bounce, where after the first interaction it is going to hit some other place. So in case of urban area, so this is your transmitted pulse, it has hit the building, but because of the adjacent features, instead of going directly to the receiver, it's going to hit another part of the building, and then it's going to receive. So your source is being illuminated by the incoming radiation for a little longer time, and because of this you will have a very strong backscatter, and your images in such kind of mechanism will appear very bright. And this can be used in the microwave remote sensing. in case of flood and all, it will be very useful because your urban area is going to be appearing bright in color, and if the streets are flooded, so it is going to appear basically dark in color. And when a vegetation is present, it is going to have diffuse scattering. So this is your incoming radiation. It's going to scatter multiple times, but it will illuminate the inner part of the canopy, but the backscatter that is going out will have a very less amount of power. So whenever there is a vegetation, you will see that it will be kind of grayish kind of texture than being bright or being dark. So this can be used for the identification of the forest and the crop cover. So this is another slide. In this you can understand. So your canopy, here it's going to have a single surface scatter. So one part of the canopy is illuminated and it's going to go to the receiver. But if you have multiple trees, it's going to have basically a volume scattering. And if there is water, if so, this is the case of flooding. So it's going to hit the water, and the water is not going to allow the microwaves to transmit. So it hit the trunk and then it's going to the receiver. So in this case, it's having a double bone scattering. So if suppose if you have a paddy crop, so initially when the crops grow, it's always going to have some standing amount of water. The paddy fields will always have the standing water in it. So initially it's going to have a backscattering, and if your look angle is such that it is going to hit one crop and then it's going to hit your water and then it's going to return back to your sensor, in that case you will have double bounce scattering. And if after your rains, if the paddy is completely flooded, you will be having a specular scattering, that is a just a single bounce. And in this case you will not be able to see anything. It will be dark because this is not going to the radar receiver, it's going somewhere else. And based on your soil moisture conditions also, the first image, the soil is dry, it's going to have a diffuse backscattering, so it's going to appear grayish in color. Here the moisture is increased, it's going to have even more darker in color, so this will be bright when compared to the second image. And if you have flooding, it's going to be dark. So this is how the microwaves interact with the objects on the earth. So these are the three different mechanisms. Next is the roughness and its scattering. So the amount of backscatter strength that is received by the radar is a function of your roughness. So if it is a highly rough surface, it's going to have a very strong backscatter because multiple reflections will take place. And this whether a surface is rough or smooth depends on the wavelength of the uh, band at which you are operating. So if I say, for example, here it is given. So a surface may be rough for X band, but the same surface may be smooth for L band because X band your wavelength is less and L band has a higher wavelength. So how this classification is done? So if your roughness height is greater than half of your wavelength, that surface is going to be rough. If it is between lambda by 32 and lambda by 2, it's going to have a moderate return. And if it is h less than lambda by 32, it is going to be a smooth surface. And there is another condition, Rayleigh roughness and Fraunhofer roughness. So these are the other two conditions that are also used in addition to this to classify whether a surface is very rough or smooth for a particular wavelength. And next part is your wavelength and the penetration power of the microwaves. So as the wavelength increases, it's going to have a high penetration power. So X band maybe your from the top of the canopy, it's going to just reflect back. It's not going to penetrate inside your canopy. Your C band will have an intermediate penetration, and your L band is going to completely penetrate. And you have another band also, P band. It can even penetrate the surface to a certain depth. So this is in case of dry alluvium, and this is in case of snow and ice. So you, based on the wavelength, your penetration power is going to increase, and different applications are there. So P band may be used in case of defense purposes. L band is used for maybe used for the soil moisture assimilation studies. C band is what we mostly commonly use for our water resource engineering purposes, and X band is suitable for the um, determining the cloud movement and cloud cover. So if there's going to be water laden clouds, so it is going to be reflected in your X band radar. So you can see there are X band meteorological products that are available. So we can use that for our analysis. So this is one of the sample image. So this is Sentinel-1 C-band radar image, and it is a backscatter coefficient, that is your sigma naught, in VH polarization. I will explain the polarization. Don't worry about it now. So VH polarization. So this is near Chennai, and this is the Chennai airport. So you can see the reservoir surface is smooth and it's appearing dark. Your runway is also smooth, that is also appearing dark. And this is a dense urban area, and this is one of the rivers. Your dense urban area has a very high backscatter because of the double bounce thing. And this last image, what you are seeing is the IIT Madras campus. It has a lot of forest cover. So when compared to the urban area, you can see how the vegetation is having a little diffused scattering. It's grayish in color. So this is in VH polarization. And different polarization will have a different effect on how the image is looking. So if I go to the next image, this is VV polarization. So you can see the difference. So this is very dark. So in VV polarization, what happens is, whatever the vertical features, if there is a lot of high-rise buildings, those buildings will be reflected in the VV polarization very well, because it is vertical transmit and vertical receive. So whatever is the vertical features that are in the terrain, that will be highlighted more in this particular polarization mode. So your water body is appearing smooth, and your runway is appearing dark. Your urban area, when compared to the previous image, it is it has become a little more diffused. And this is IITM campus, and you can see the patterns in this. If you do a textural analysis, you will be able to classify what kind of crop is available. So next part is the polarization. So polarization refers to the locus of the electrical field vector in a plane perpendicular to the direction of the propagation. So if you let's say if this is the one of the electrical field, and you pass it through a polarizer, and such that it allows only the vertical features to pass through, and blocks the rest of the directions. So your output is going to be, with respect to the axis, you will have only the vertical uh, electrical field. So rest of your hello, hello, okay. So your rest of the field vectors will be blocked by that particular polarizer. So you will only have the vertical field, rest will be blocked. So similarly, our radars can be designed in such a way that it will receive either vertical or horizontal. So whatever the Sentinel-1 image that showed, it operates in two modes, VH and VV mode. So we can see how the polarizer works. So in the radar, we have different combinations. So the four primary combination which any of the microwave satellite uses, HH, VV, HV, and VH. So which means you're transmitting pulses in the horizontal direction, but you're receiving pulses in the vertical direction. So I will show one animation, you can understand that. And the first two categories, they are called as light polarized, and the last two categories, they are called as cross polarized, because you have a horizontal transmit and a vertical receive, and they are orthogonal to each other. So if I say microwave data is single polarized, it will be HH or VV or HV or VH. Any one image only you will get. And if it is a dual polarized, you will get two set of images. You will get HH and HV, VH and VV, or HH and VV. So these are the three set of data that you may expect when you are going for a dual polarized image. When you say sensor is fully polarized, you will get all the four polarization. You will get four images for the same area. So other combinations that are available is this is available in the RISAT one. It is fully polarized, and it is also able to send right circular polarization and left circular polarization. I will show what is right circular and left circular. So you will get RH, RV, LH, LV. So this is another two set of data that you can expect. So you can visit this particular link where the animation is described very well. So you can see. So let's say this is a vertically polarized. So this is a vertically polarized electromagnetic spectrum. So this is the first wave. So this is horizontal transmit. If I say this is vertical transmit, if I say horizontal receive, your radar is going to receive this kind of a signal. So it's going to be horizontal with respect to the axis of propagation. So this is when I say that it's going to receive horizontal and horizontal, so it's going to HH. So which means this is your transmitting and this is your receiving. So both will be horizontal. So you will not notice any difference. So if it is again vertical and vertical, it's going to be the same. So if I say H and V, I am setting this to horizontal and the second wave as vertical. So it is going to transmit vertical pulse and it's going to receive the horizontal pulse. Similarly, you can have vertical and horizontal. And last two things which I showed you is right circular and left circular. So this happens when your difference, when the phase difference between the wave 1 and wave 2 is at 90 degrees. So I increase my phase difference to 90 degrees and then I'm going to add both. So what you are seeing here is right circular, right circular polarization. So it is going to transmit a circular polarization. So it's not going to be horizontal or vertical. It will transmit this, but it's going to receive either horizontal or vertical. So it will transmit circular, but it will receive either horizontal or vertical only. So if I give polarization this as vertical. So this is going to be your left circular. So it will transmit this kind of polarization, the transmitting pulse. So this phenomenon is this polarization is very useful for interferometry. That is one type of study. I will describe that. So anybody is having any doubts in polarization? Okay. And when you are using a microwave remote sensing data, similar to your optical remote sensing, this is also going to have some geometric distortions. So the first distortion is the foreshortening. So when you are measuring any rugged terrain such as mountains, in foreshortening, what happens is your base of your mountain is going to appear very close to the top of your mountain, but in actual case it will not be like that. It will have some more distance, and because of that your illuminated part of the mountain will appear as a very bright band. So I have the examples. I will example images. I will show that. The second kind of geometric distortion is the layover. So here what will happen is your bottom of the mountain will appear after your top of the mountain. So in reality it is not possible. So your top of the mountain will appear first and your bottom of the mountain will appear later in the image. So that effect is called as the layover. And the shadow effect is it is not able to illuminate the backside of your mountain, so it is going to appear as a shadow in your image. So to understand it more clearly, so here everything is in orthogonal directions, but actually how our radar will project all these objects to our slant ranges, it's going to have a cylindrical kind of a projection. So in the point B dash, that's your example for layover. So your bottom of the mountain is appearing later, and D dash and E dash are the foreshortening. So your top of the mountain is very close to the bottom of the mountain, so this distance is very less, and in case of shadow it's not able to illuminate. So you can see the effect of foreshortening in the first image. So your radar is looking in this direction. So this is the top of the mountain and this is the bottom of the mountain. So the distance between these two is very less, but in actual it will not be like that. And the example of layover. So this is the base of the mountain and this is the top of the mountain. So this point has to come here, but it has appeared in this particular place. So this is another effect of another geometric distortion. Then the last thing is the shadow. So your sensor is looking in this direction, and this is the top of the mountain. The bottom, the back side of the mountain is not completely visible. So now I will explain one of the interesting applications, which is interferometry. So in interferometry, the prime phenomenon is the concept of a phase difference. So this red color line, what you are seeing is the first time when the satellite has passed. So it has captured one image, and let's say it is taking one single pixel. So I'm talking about only one single pixel here. So in the first pass, this pixel has produced this kind of a face, and after some time something happened on the ground, And when the satellite is measuring the same place from the same position again, it is giving me a phase difference that is represented by the blue line. The difference between these two, that is called as your phase difference theta. So two waves are said to be in phase when the first pass and the second pass are the same. So if they are differing, something has happened on the ground. Now we need to identify what has happened. So in interferometry, phase difference is the principle. So when two SAR images of the same area are acquired at a slightly different times from slightly different positions, but it should be the same position, it's not slightly different position. The phase difference between the two images can be used to compute the topography of the Earth's surface. And this technique is known as the interferometry or InSAR. So what I am trying to say is, so this is the surface of the ground at time 1, the black pulse it has recorded. And after some time, let's say landslide happened or earthquake happened or some kind of ground disturbance has happened, your ground surface has moved like this. Now the amount of backscatter that is received by this red will be more than your what is received by this black line. So because of that, there will be a phase shift in the data, and that is what we are going to uh, use to determine if there is any surface deformation on the ground. So this is one of the case study. It was done by National Remote Sensing Center, a recently published paper. So in Afghanistan, there is a earthquake that has happened, and this is the epicenter of the earthquake, and this is the entire area, and this is the microwave remote sensing data during the ascending pass and descending pass. So which means the satellite is ascending towards the North Pole, and after maybe 20, after the revisit period, it is having a descending pass, and it has captured the same place. Now here there is a new term called as coherence. It refers to the degree of similarity or correlation between the phase information in the two radar images acquired at different times. So whether these two data are having any correlation or not, how similar these two data are. So that is what coherence refers to. And after some analysis, they make this differential interferogram using a software called as NV, and it has a package called as SARscape. And by using that package, you will be able to generate what is called as interferogram. So this is similar to your contour lines, but here what you will see is when something has happened on the ground, you will find some distinct pattern that appears, some rings like this. So these are all the natural topography, and it will have a random interferogram. But when something has happened, so it will have a distinct pattern like this. So these are the patterns that we are going to make use of. So this is another place. This is in the descending pass for the same place. So it has produced the interferogram, something like this. So something has definitely happened in this region. So when we try to analyze the data, and we will be able to produce displacement maps. So which means how much the ground has moved. So from one time to another time, what is the displacement that has occurred between these two times. So, and after you plot the displacement map, you can see there is a displacement of 0.38 meters in the red part, that is positive, which means the ground has come up. And your minus displacement means your ground has gone down. So, earthquake happened, some kind of movements happen, and your ground is now displaced. Now, if you see the interface between these two, so you will be able to locate your fault lines. So this is one of the application, and this is an ascending pass, and this is the descending pass. And further, what you can do is you can also plot with respect to the east-west direction, how much it has displaced. So how much it has gone into the east-west. So considering this kind of uh, image, most likely your ground has this ground has moved this way and this ground has moved this way, and whatever the features that were present here, they all lost their original positions, because of which there is a phase difference that has occurred in your data. And by analyzing this, you will be able to find out what kind of displacement that has happened. There is another study that also happened recently, Joshimath and Uttarakhand. Similar analysis they have done, and they have mapped how much the slopes have moved within a very short span of time. So you can search for that paper and you can see how this application is available. So to analyze the SAR, that is your synthetic aperture data or the microwave data, uh, National Remote Sensing Center, they have developed a tool called as the SAR pole tool to analyze the data of RESAT 1, RESAT 1 and RESAT 2. And I think next year they will be launching another microwave satellite, NISAR. So NISAR will operate in S band and L band. So you can analyze the microwave data by using this QGIS plugin. And if you are using Sentinel data, you can use Snap Toolbox. These are open source softwares. You can try. Pulsar Pro is also another tool that is also developed by the European Space Agency. You can. These are the links for the download. And SAR poll tool, I think I was not able to find the link. I will put up whenever I get it. And SARscape in NV. NV is a commercial software. It's not open source. You need to pay for the software. Then only you'll be able to do the analysis. So these are all the sources. And thank you. So anybody is having any doubt related to microwave?
Sir, for that